Okay, so we're going to talk about the periodic table today, a little anatomy of the periodic table. You're probably going to want to get one of the new periodic tables off the front counter, off that little podium up there. Get yourself some colored pencils or markers or whatever you have. There's colored pencils up on the front counter also, because you're going to want to highlight and sort of emphasize specific areas of the periodic table as I talk about them. It'll help you with formula writing at the end of this semester, and then it'll help you in the spring semester. But first, we're going to talk about my grocery shopping. Um, for Thanksgiving coming up, my thing is I have to make the pumpkin pie and the mashed potatoes. So I need a bunch of stuff. And what I like to do before I go to the grocery store is I make a grocery list. And then I like to make a PowerPoint slideshow of the layout of the grocery store. And then I sort of mark where I need to go. I know that it seems like it would save time for me to just go and get everything, but I like to spend a couple hours making a PowerPoint slideshow and a video, and I think that probably saves me time, because otherwise, how would I spend 2 hours shopping for my ingredients? Nonetheless, that's what I do. Okay, so here's a layout of the store, and the neat thing about grocery stores is they don't really just randomly throw stuff. They don't have a big semi truck deliver a bunch of food to the back of the store, and then they just put it wherever they have an opening. They sort of lay things out, and basically all grocery stores all over the world do it the same way. They sort of organize things in a way so that you basically know where the items you want are. Okay, and they kind of group things together. Well, here's my list. I'm going to go into the store. I need potatoes, milk, canned pumpkin, all this kind of stuff. Well, I'm not going to go get the potatoes first. I'm going to go over to the baking aisle and I'm going to get my canned pumpkin. And it turns out what's neat is the next thing, the flour is in the same aisle, just a little further down. And boy, they put sugar in the same aisle, and vanilla, and with the vanilla, the flavorings and the spices, they have ginger, nutmeg, and cinnamon all in the same row. This is awesome. I'm getting a lot of my stuff done right here in the same aisle. Oh, and the sweetened condensed milk with sugar, all cooked down. Onions aren't in this aisle. Butter, no. Whipped cream, bread. Oh, marshmallows in this aisle. I'll go ahead and grab those. And if you'll notice that these are all things you use for baking. Spices and canned and sugar and flour. They kind of all keep them together so that you basically know where things are. They make it easier for you to find things. Everything in this aisle is similar. It's all used for the same purposes. All right, well, okay, I'm still not going to get the potatoes, but my milk is up here, okay. Oh, and look, in the same aisle I get the eggs, and just real close is the butter and my whipped cream. They're all right there together. So they've kept all this whipped cream, butter, milk, everything based on milk, they sort of keep in the same area. Okay, my bread is nowhere near any of them. It's a baked good. It's not in the baking aisle. It's already made, but they keep it over with all the other donuts and cookies and things that they have actually made. Now all I need is my onions and potatoes, and I can get out of here. Well, the good thing is they keep the onions and potatoes together. They're down in the produce aisle with all the other plants and things that are grown. And the reason I've been doing this for you is that this layout of a grocery store could actually be called the periodic table of the grocery store, because a periodic table is just like a grocery store. It's not random. Things are placed in the periodic table in a specific position because it's grouped with other things like it. A periodic table has a baking aisle and a produce aisle and a cookie aisle. Similar elements are grouped together in aisles. Okay? Now, so let's talk about the periodic table, our grocery store of elements. This is what it really looks like, but that's not really how you usually see it. What they normally do is you'll notice that these two rows here in the middle, they usually take those out and stick them down at the bottom. Then they shove these two ends together. And the reason they do that is, well, this doesn't fit on a piece of paper neatly. You'd have to put it on both sides of the paper. So they take this out, squeeze these together, and now it fits nicely on a piece of paper and you can see it. You just have to remember that those two rows belong in the periodic table. So let's start talking about the aisles of our grocery store here of elements. Well, these vertical columns are called groups on the periodic table, and they're like aisles in a grocery store. Everything in group 1 has one valence electron that it tends to lose to become a +1 charge. That's what the +1 is at the top. It's the charge that hydrogen, lithium, sodium, potassium, rubidium, they're all similar. All of these things are explosive in air when they come in contact with oxygen or water. They catch fire and explode. Everything in group 2 has a +2 charge, 2 valence electrons that they like to lose and become a +2 charge. Beryllium, magnesium, calcium, strontium, they're all in that group because they're all similar. You'll notice that calcium's in there, that you have a lot of calcium in you and your bones. And in fact, all these things are so similar, if your body didn't get enough calcium, but it had magnesium and strontium or beryllium, it would actually use them to make your bones. They wouldn't be perfect because the atoms aren't the same size, but it would use them if that's all it had. Everything in the middle, so here we have the +1, the +2 group, and we'll go ahead and skip the whole big middle there and move on over to the +3 group. And +3, and I'm going to stop at boron, but boron likes to form a +3 charge, but it's actually fairly similar to everything below it in the group, but I'm going to stop it right there. And I'm going to move over to the carbon group, but we're going to stop at carbon and silicon. And I'm stopping at, you might remember the staircase in the periodic table. Carbon and silicon are very similar. They both like to form either ±4. They make 4 bonds, and your body can actually, if it doesn't have carbon, silicon can be used. It's not perfect, but it can be used to form those bonds that make up the bulk of your body. The -3 group, nitrogen, phosphorus, and arsenic, and again I'm stopping, I'm going all the way down. Oxygen, sulfur, selenium, and tellurium are all similar. They're in the same aisle. You can think of it as the candy aisle if you'd like. The halogens, this 7th group down here, they have 7 valence electrons. They like to form a -1 charge, and they're all similar. They all have the same charge. And then you all know the noble gases. They're all similar. They're all over in their own aisle of our grocery store. They don't like to do anything. They're not reactive. They all have their 8 valence electrons, so they're all happy. They just don't do anything. So this is our grocery store of the elements. Now, we're going to talk a little bit about the anatomy again. Not only are they grouped similarly top to bottom, but it's a periodic similarity. The periodic table is basically set up to count protons. Hydrogen has 1 proton, and if you read the periodic table like a book, left to right, top to bottom, hydrogen has 1 proton, helium has 2, lithium has 3, beryllium has 4, boron has 5 protons, carbon has 6 protons. Left to right, top to bottom, it is a count of protons. And that's the important number, the atomic number. Carbon has 6. If it were to undergo some nuclear decay where it only had 5 electrons, it would no longer be carbon, it would be boron. If boron lost a proton, it wouldn't be boron anymore, it would be beryllium. Things are what they are because of their proton count, and the periodic table is organized that that proton count simply counts up, left to right, top to bottom. And it works everywhere, even down here in the bottom. I'll put the box around cerium here, or cesium, sorry. It has 55 protons. If you keep going to the right, there's barium with 56. But you'll notice if you keep going to the right, 57 isn't the next one, it's 71. But you have to remember that these 2 rows at the bottom actually belong in the body of the periodic table. So it really does count left to right. It just goes from cesium at 55 protons to barium at 56 to lanthanum at 57, cerium at 58, praseodymium at 59, and then it just keeps counting up all the way down into ytterbium at 70, and then it continues on with lutetium at 71, hafnium at 72, and then it just keeps going. So it is a count of protons, an increasing count of protons with the vertical columns being aisles in a grocery store, atoms grouped by because they're similar to one another. Now we're going to divide the periodic table into two groups. And we're going to do that with that staircase that you hopefully remember from middle school. It is the dividing line between metals and nonmetals. Everything to the left of the staircase, except hydrogen, is a metal, and everything to the right is a nonmetal. Metals are good conductors of heat and electricity. That's how we define a metal. And we don't always think of metals as being soft, but all pure metals are soft. You probably know gold is soft, silver and copper are kind of soft. But iron is also soft. You can cut it with a butter knife. You can bend it. But we often think of iron as being steel. Well, steel is a mixture of iron and carbon. The carbon makes it hard and strong. Pure iron is soft. Pure calcium is soft. I know your bones are not soft, but that's because the calcium is mixed with other things. All metals are soft, ductile, and malleable. Ductile means that they can be pulled into a wire like chewing gum. Malleable means they can be pounded into sheets like aluminum foil, tin foil, somebody taking iron and pounding it into a steel drum, or pounding copper in art class. That can be done because metals are soft. And everything to the left of the staircase except hydrogen up here in the corner is a metal. And nonmetals are everything to the right, including hydrogen of the staircase. And they are, you don't think about nonmetals, you always think they're gases, but in the solid phase, they're all brittle. Solid oxygen hit with a hammer shatters. Carbon, like diamonds, pure carbon. If you were to hit a diamond with a hammer, you shouldn't do that because it'll just shatter to dust. Metals are the soft one, and nonmetals are the brittle, hard ones in the solid phase. Metalloids are the things that sit on and above and below the staircase. And remember that metals conduct heat and electricity. Nonmetals do not conduct heat or electricity. Metalloids kind of conduct heat and electricity. And that's important to us in the modern technological world. Computers at their heart, and your phone and calculators and whatever you have, what they do is count electrons. Well, you can't use metal processing chips because they count every electron. They just let all the electrons flow. You can't use nonmetals because they don't let any electrons flow. Metalloids are used because they let some electrons flow. Remember that computer chips count electrons. Either an electron flows through the processor or it does not. It's a 1 or a 0. And that's the binary code of computers. An electron flows or it doesn't, 1 or 0. Metals let them all go. Nonmetals don't let any of them go. Metalloids let a metered, countable amount of electrons flow through them. And you probably know this, but computer chips are made of boron, silicon, germanium, arsenic, antimony. And a lot of them are actually poisons too. That's another way that these things have in common, so you shouldn't eat computer chips. But they're in common because they kind of conduct electricity. Alkali metals are this first group, the +1 group or aisle in our grocery store. The alkali metals are the +2. They're all similar, beryllium, magnesium, calcium. They all act the same way, and they all have a +2 charge. The transition metals are this big group in the middle, including the 2 rows at the bottom. And their thing, again, is that they form multiple charges. Group 1 is always +1. Group 2 is always +2. The ones in the middle, the transition metals, many charges. Schnapps are the elements of life. CHNOP and S. I think I wrote 99, but I think it's about 95% of you are these 6 elements. You obviously have iron in your blood and calcium in your bones, but most of you is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And you can mark this if you like on the periodic table. The halogens, I don't know why they're called the halogens, but it's this group, fluorine, chlorine. You have some of these in your body. And then the noble gases, this last group or aisle in the grocery store over here. The lanthanides are the group, the first row. If you'll notice 57 here, La is lanthanum, and these are the lanthanides. The next group, actinium, is called the actinides. So everything after actinium in this row are called actinides, and they're all similar to one another.